All right, I just finished recording all of the notes, and I went through them pretty slowly and in detail, and then the computer messed up and the video got destroyed. So I'm going to go through the notes again. I'm going to do it fairly quickly, and I'd like you to listen, and then periodically I'm going to say pause the video and copy down what I've covered. So at that time, please pause the video and write down in your notebooks what I've covered, and then once you're finished writing that down, unpause the video and listen again, and you'll have a chance to both listen and attempt to understand, and then you can get this down so you can look at it again in your notes later. The notes are on fusion and fission reactions and on mass energy equivalence, E equals mc squared. And we're going to start out with fusion and fission reactions. A fusion reaction is when two small nuclei combine to make one large nucleus. Fusion reactions are something that we have attempted to do on the Earth but have not been very successful. Fusion reactions are very difficult to produce. They are produced quite well on the Sun because of the Sun's immense gravity and immense heat. But unfortunately, we don't have those conditions here on the Earth. Fusion reactions produce less radioactive byproducts. And so they are good in that they produce energy, clean energy, with not much radioactive waste. And so this is something desirable that we would like to be able to do on the Earth to produce power. Right now we have to produce power using fission. So fusion reactions occur typically on stars. Also, we've been able to do this uncontrollably with hydrogen bombs. Fission reactions take large nuclei like plutonium and uranium, and the reaction splits the atoms into smaller nuclei, which become radioactive waste that we have to store. Not that it's any worse than carbon dioxide and carbon monoxide, but it is not very desirable. So we're talking about fusion reactions and fission reactions. You need to know the difference. So fusion reaction for the Sun, here's an example. You should be able to read this. This is radioactive atomic notation that we learned last time. Here is a hydrogen isotope. It's hydrogen 2. It has 2 nucleons, atomic mass 2, and it has 1 proton. Normally hydrogen, the normal flavor of hydrogen, just has 1 nucleon. Here's a regular hydrogen. This is the hydrogen isotope, hydrogen 1. This is hydrogen 2. In a fusion reaction, these combine to produce helium-3 and energy. How do we know how much energy? Well, if we mass the reactants and we subtract the mass of the products, we have lost energy, or lost mass rather. The reactants weigh more than the products. Where did the mass go? It turned into pure energy. If we know the mass lost, we can apply it to E equals mc squared and calculate the energy. That's what we'll do later. Here's another fusion reaction. Helium-3 plus helium-3 fuses into helium-4, and it also produces 2 hydrogen-1 nuclei, plus energy is liberated. The mass of the reactants is greater than the mass of the products. So mass was lost. It became pure energy. Okay, last one, and then I'll let you copy down these notes. Fission reaction, a uranium bomb. Uranium-235 gets hit by a neutron. This happened in the PhET lab. It breaks apart into krypton 89 and barium 144. And it produces 3 extra neutrons, which, by the way, hit 3 more uranium-235 nuclei, causing a chain reaction. In addition, energy is liberated. The reactants weigh more than the products. Mass has been lost, and the lost mass is equal to the energy gained through E equals mc squared. Okay, let's copy this down, and I'll go back up to the top. Please pause the video. Now that you're unpaused, I'll move it up. Pause the video again. Right, now that you're unpaused, I want to explain what I've got down here. If you do not have one of these elements, let's say I want you to balance this equation and I'm missing the krypton, you can figure it out just like you figured out the missing nuclei from radioactive decay. First of all, the protons, or the atomic numbers, have to balance on the right and left side. So we have 92 plus 0 equals 92. And if I only know the 56 and I don't know the 36 from krypton, I know 56 plus 0 is 56. And 92 minus 56 is 36. Also, the nucleons balance. I have uranium-235, which has an atomic mass of 235, plus a neutron, which has an atomic mass of 1, gives me 236 nucleons. If I don't know the krypton, I know that barium has 144 nucleons, plus 3 neutrons is 147. The difference between these two is the number of nucleons in krypton. So 236 minus 147 gives me 89. Okay. Let's see. We're going to flip over to the other side, and I need to take care of one thing on my computer. The network's about to shut off. So I need to unplug my network cable so it doesn't shut my computer off. Okay, mass energy equivalence. I flipped over to the left side. Mass energy equivalence is the theory that mass equals energy and energy equals mass. Einstein's famous for this. E equals mc squared. This energy, measured in joules, is equal to the mass in kilograms times the speed of light squared. As you can see just by looking at this, if you have a mass of 1 kilogram multiplied by the square of 3 times 10 to the 8, that is a huge number that you get on the left side. So just a small amount of mass will give you a huge amount of energy just because of the square of the speed of light. So in nuclear reactions, mass is lost. In the form of energy. So how do we do this? Well, first of all, we're going to have to look up the exact masses of isotopes that are involved in the reactions. We have to be a little more careful about the masses, and we need to be more precise about them. And so I'm going to try to give you a good example of that today. Here is an example of a fission reaction involving plutonium-239. Plutonium-239 has the atomic notation of this. It has a fission reaction when a neutron is shot into its nucleus. So there's the symbol for a neutron. And through this fission reaction, we have three things produced: strontium, 88, and barium 138. And 14 neutrons. Plus energy. We need to be able to figure out the total mass in the reactants and the products so that we can find out the mass lost. So that's really our initial goal: find out the mass lost. So the way we do that is we need to look up the masses of all of these different nuclei or species. And so I've given you a periodic table that's a little more complicated than the normal periodic table. It has the masses of different isotopes. And so we need to look at those. We need to be careful about it. First of all, we're going to look up the mass of the plutonium-239. And I'm going to write that down here. M of Pu-239 equals, and then here's our periodic table. Here's plutonium. Let me zoom in. And plutonium-239 has got a mass of 239.0522. So 239.0522. It's really important that you write all of the precision out. Next, we have a neutron. So what's the mass of a neutron? Well, we can't look on the periodic table, and so I'm going to give you the mass of the neutron. A neutron all by itself has a mass of 1.0087. You probably thought it was just 1. Well, that's because most periodic tables don't have the precision that my periodic table does. Next, we need to know what is the mass of strontium-88. And so we're going to look again at strontium-88. And if you look here, here's strontium. We're going to zoom in. And strontium-88 has an atomic mass of 87.9056. And we next need to look up barium. The mass of barium 138. Barium 138. It's right below strontium. And it is 137.9052. Okay, that's all of the different species. We have some more neutrons over here, but they have the same mass as this neutron. And we're going to figure out what is the mass. So we add up the reactants on one side, and it's going to be 239.0522 plus 1.0087 equals 90.9317. You know what, that's not the right, that's the wrong number. Let me put a line through that. No problem. We need strontium-88, which is 87.9056. Sorry about that, I was looking at some different notes. And we're going to add to that the barium-138 mass, which is 137.9052, plus 14 neutrons, which have a mass of 1.0087, plus mass lost. So we have this extra bit that we know is going to get lost. We need to solve for this mass loss. So we're going to add up this side and all of these numbers, and then we're going to subtract these from this. So if you add up this side, you get 240.0609. And if you add up this plus 14 times this, you get 239.9326 plus mass lost. Now obviously this number is smaller than this number. We're going to subtract 239.9326 from both sides, and if you do, you get 0.2829 equals mass lost. Now from chemistry, you know that all of these units are either atomic mass units, or if you're dealing with moles of these particular species, then you're dealing in grams. So we're going to write down grams. We're going to say this is a mole of plutonium, a mole of neutrons, and so forth and so on. Now, the next step, convert from grams to kilograms. And we do that by multiplying. By 1 kilogram over 1,000 grams. That's our conversion factor. If you do that, you get 0.12829 grams times 1 kilogram over 1,000 grams. Grams cancel, and you end up with mass in kilograms, which is 0.000128229 kilograms. That's not a whole lot of mass. It's 1.2 thousandths of a kilogram. A very small amount. Now we're going to use E equals mc squared. To get the energy equivalence. So we've got 0.000128229 kilograms times 3 times 10 to the 8 meters per second, all squared. Remember, we're not squaring seconds, we're squaring 3 times 10 to the 8. This is equal to the energy. So the energy is equal to 1.15461 times 10 to the 13 joules. To give you an idea what that is, it's 11,546 100 000 joules, which equals about 11 trillion joules. That's a lot of energy for 0.1 grams of mass.